We're talking about increasing and decreasing functions. We're going to focus on intervals of increase and decrease. Now, what do I mean by increasing and decreasing? Well, increasing, a function is increasing when successive values of x have y values that are getting larger and larger and larger. So as you move from a small x up to a larger x, the y values are also getting larger. So the graph is literally climbing from left to right. So here are the x values that are represented by the graph I'm showing here. And as we approach 0, or as the x gets larger, the y values here also get larger. You see that? Yeah. So the graph is climbing from left to right. Now it comes to a point here where it kind of levels off for a brief second, but it doesn't ever drop and start to go down. It keeps going up. So as x continues to increase, y continues to increase. So this is a graph of y equals x cubed, and as we can see, from left to right, the graph is increasing over what interval? What interval? Remember we talked about interval notation now. So where is the graph increasing? Negative infinity. Okay, that's not an interval. Negative infinity. What else are you going to say, or what else we need to?
Negative infinity points, negative infinity.
Negative infinity to what?
Point and negative infinity.
Okay. Negative infinity?
Infinity.
Positive infinity.
Why is it positive?
John,
Okay.
come on, are you
So
gonna ask him to go home?
negative infinity is as far as you can go to the left, right? So really, it's increasing from everywhere on the x spectrum there.
Yeah.
The entire domain. How do you express the entire domain? In interval notation, negative infinity to positive infinity. From as far left as you can go to as far right as you can go.
Oh, okay.
Infinity, okay? So where is it decreasing? Nowhere. And how would we say nowhere? One of the ways you could say this is you could put a little, you could put a little empty set there, okay? Empty set. There is no interval on the domain where it's decreasing. All right? So over the entire interval, entire domain, it's increasing. Now, this one's a bit different, though, isn't it? I've got these little marks on here. You see the blue marks, right? As x increases from negative infinity over here, because this continues up, right? So as x increases, the values of the function get smaller and smaller and smaller until x reaches what point?
0.
Yeah, until x reaches 0. So this is the function x squared minus 3. It's a parabola that opens up normally, and it opens upwards normally, but it is shifted down 3 units. So 1, 2, 3 units. So yeah, it decreases until x equals 0. So let's write what we've got so far. It decreases from negative infinity all the way up to 0. Now we'll put a round bracket there, okay? At 0, it's neither increasing nor decreasing, really, because if you think about it, the graph's coming down like this, and what is this?
0.
Is 0 positive or negative? Right? Like it's like, so we'll use a closed bracket, not including 0, really, and not including negative or positive infinity, because it's not an actual number, right? It's a concept, infinity. So where is it increasing then? What would be the interval that it's increasing?
0.
Yeah, so starting at 0, or just right beside 0 there, right? We won't include 0, but after 0, so when it's positive. So from 0 to infinity and beyond. Right.
There's beyond?
There's beyond infinity? What?
Is it a thing?
Well, if you watch Toy Story, there is.
Google.
To infinity and beyond.
Oh.
You know the guy that flies, the Buzz? Forget it. Okay, so we've got an interval where it's decreasing and an interval where it's increasing. Okay. Now what about this one over here? This is y equals x plus 1, this graph right here. So it's increasing,
All the time.
again, everywhere, right? So from negative infinity to positive infinity. And it's decreasing nowhere.
So why would the ones on the second one, when it gets to 0, not have like this square bracket?
Okay, so the question is, why would this not have a square bracket? Because at a single point, It's not really increasing or decreasing technically. And if you think about you know, 0, is it positive or negative, right? If you're coming to a stop, when you've stopped, are you going forward or backwards? Well, it doesn't really, you know what I mean? That kind of question doesn't really make sense, so we'll just use a round bracket. Plus, we couldn't include 0 here and include 0 here. And why would we include 0 in one interval and not the other? So, just to make it easy, we won't include 0. But that's a good question. Yeah. Okay, let's continue on with the lesson here. So, now the question is then, if we look at these graphs, okay, so here's what we want to move to. We want to think in terms of slopes of tangent lines, or derivatives, okay, derivatives. So how are the slopes of the tangent lines related to whether the functions are increasing or decreasing? So let's take a look. Well, maybe you can see from this, but I'm going to give you a new graph here, okay, and I want you to copy this graph down, just sort of roughly what this graph looks like here, and we're going to make x1, x2, and x3 be the x value that represents this maximum point and this minimum point for x2 and another maximum point here. And then the graph just continues on in a downward direction to a negative infinity and so on, okay? So recreate this. And then what we're going to do is we're going to try and identify intervals where the function, f of x here, where it's increasing and where it's decreasing. Okay. So the function, let's say, is increasing. Where on this graph? Where is it increasing? Okay, from negative infinity, okay, yes, to x1. Okay, so from negative infinity, right here, increasing, to x1. Good. That's right here. So any other points, or any other, intervals? Oh, very good. x2 to x3 over here, yeah. Okay, and we'll put in union with x2, comma, x3. Awesome. All right, so let's take a look at those. Those are the two parts of the domain where the function is increasing, correct? So let's take a look at the derivatives. So if I just draw some random tangent lines here, okay, just random in these intervals, there, okay. What do you notice about all of those tangent lines? Their slope is positive, yes, very good. Slope is positive. That is very, very important. So on the intervals where a function is increasing, we also notice that the slopes, that is the values for the slopes for the tangent lines, or the values for the derivative, are 0. They are greater than 0 or positive. Okay? That's increasing. That's very important to notice that. That's awesome. And so let's talk about decreasing then, right? Decreasing. Well, we're decreasing on, and I'll use the black for decreasing. We're decreasing from x1 to x2 here. And I'll draw some tangents, which don't look very good, but x1 to x2, as well as in union with x3 and on, right? x3 to infinity. And you don't have to put positive infinity. If you don't put a negative, I'll know what you mean. So what about those derivatives? Does it make sense that those are all negative? Yeah, not 0, but they're negative. Yeah, but it's less than 0. So the function is decreasing whenever the derivative is less than 0. Now what happens at 0? F prime of x equals 0. What happens there? So that's when the slope is 0. What do those represent? Right there? Okay. That's where they are neither increasing or decreasing. Good. You're learning from a few minutes ago. That's great. But what do these points, why are these points significant where they have derivatives of 0? Those would be the what? The constant? Why are these points significant in this little explanation here?
x1 f5 would be 0.
Okay, so if I do this, this is where the intervals start and stop. That makes sense, right? So x1 is a point where the interval changes from increasing to decreasing. x2 is where it changes from decreasing to increasing, and so on. So that's going to be important. F prime of x equals 0. That means that we have a 0 slope, and those would represent, in this case, they would represent maximum x values, maximum points, or minimum points, right, of the graphs. And they would also represent the points where the function changes from increasing to decreasing. Now, there are other things that represents, but that's what's important, what we need to draw from this example. Okay? All right? So, when the derivative is positive, the function is always increasing. Always increasing. Where the derivative is negative, that's where the function is decreasing. Where the derivative equals 0 represents points where they change. It changes from increasing to decreasing. Okay? And again, there's more to this, but that's what we can learn from this example. That's where we'll start. Okay, so filled this in already, so I left that blank, but we can skip over that. All right, so if we have the derivative, we can perform unit analysis that we reviewed the other day on the derivative to determine where the graph, or f of x, is increasing or decreasing. And then, so what this is, we're beginning to analyze functions using calculus methods to be able to sketch them. Okay, so this is chapter 4. We're talking about mainly it's called optimization. All right, now that's kind of the first step. But chapter 5, we're going to get into curve sketching. So we're going to analyze a function without knowing what the graph looks like. We're going to be able to put all these pieces together, calculus stuff and non-calculus stuff, and we're going to be able to draw a very accurate sketch. And so one of the things that would be nice to know is where the graph is increasing, and where it is decreasing, so we can kind of start to draw it. So if we can have, these sections identified, we have a good idea of how to draw it. So again, back to the sign analysis here. All right, we want to find out where the derivative is positive and where the derivative is negative. So here's a question. I apologize for the messiness here. I've kind of got this started. I'm going to give you the derivative in factored form and make this really, really easy. Okay? And I'll just kind of back off some of this so we can do this together. So write down this question. I'm going to give you a few seconds to do that. All right. So if we're given the derivative in this form, in factored form, and we don't have to be given it in factored form, we can actually factor a larger polynomial into factored form. We've done that as well in pre-calculus. May need a reminder on how to do that, but that would include guessing what some of the factors might be as far as binomials, and then doing synthetic division real quick to see if it's a factor, remainder theorem, factor theorem, all that sort of stuff. So, yeah, don't look at me like that. I'm sorry, but you learn this for a reason, and this is why. Okay. So, but I'm giving it to you in factored form. So what we're going to do is we're going to do sign analysis on this, because I would like to know, is it frozen still? I would like to know, thank you, where the derivative is positive, because that corresponds to where the function is increasing, going upwards, and where it's negative, because that corresponds to a decrease. So let's do sign analysis again. You guys love this so much.
Oh, yeah.
Right? Right on. And let me just make a little bit of space here so that I don't give away all the answers. Oh, there it is. Okay. So x plus 3, that's going to be 0 at x equals negative 3, right? So before that, so when x is a greater negative, like negative 10, the answer is going to be negative still. So all the x values less than negative 3 make this factor negative. Anything that's larger than negative 3, like 0, if we were to plug 0 in there, 0 plus 3 is positive 3, so it's positive to the right. Okay, so that's how we know where this factor is negative and positive on the number line. We do the same thing for the other factors involved. So x minus 2 over here at positive 2 is where this one is 0, right? 2 minus 2, 0. And so anything less than 2 makes this negative, and anything greater than 2 makes this positive. Now 2x minus 7, okay, at negative 7 over 2, right? So negative 7 over 2 is negative 3.5, so here's negative 7 over 2. And that's where this one is 0. It's negative before that, and it's positive after that. All right, so tell me if you're lost right now. Just be brave. Tell me if none of that makes sense. Going once, going twice. Okay. All right, so that's how we know where on the number line each factor is either positive, negative, or 0. So now let's figure out, and again, we don't need any numbers. We don't need any values right now. We just need signs like S, I, G, and S. So negative times negative times negative is
Negative.
negative. Two negatives are positive, times negative is negative. Okay? So a negative times a negative times 0. 0. Negative times a negative times positive. Positive. So again, in between here, from here to here, it's, if I multiply these signs together, a negative times a negative times a positive, that is a positive result. Again, 0 at negative 3. What have we got here? Negative. 0 at 2, and all positives multiplied together are positive. Okay, so we are starting to paint a good picture here. So watch this. Okay, now if I were to actually just sketch out some derivatives or sketch out some tangent lines that have positive and negative slopes and 0 slopes, watch what happens. This is actually kind of cool. So I'm going to do negative slope here for a tangent line. I'm going to do a 0 slope here. I'm going to do a positive slope here. I'm going to do a 0 slope here. And then I'm going to do negative, 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 negative to a 0 here. And then positive, positive forever. Now, what this means is that the function here is going to be decreasing, because that's got to be, right? It's got to be a tangent line. And then the function is going to be 0 here, or it's going to reach a minimum because it's going from negative tangent line slopes to 0 to positive. Then we come up with 0 again here somewhere. And then these are all negative, and then 0, and then positive. So you see, we can now picture what the graph sort of looks like, right? And that's what's going to be important. So this question, though, doesn't ask you to graph anything. It just asks you state the intervals of increase and decrease. So what you would do is you would take this information now, and you would say the graph, okay, because we've taken a look at the derivative, the graph itself is decreasing, and you can just pick one or the other. It's decreasing wherever the derivative is negative. So these are the two intervals that you need to identify. So from negative infinity all the way up to, what is this x value? Negative 7 over 2. That's the first one. That's right here. That's right here. See that? Negative. And also from negative 3 to positive 2. That's this middle one. So that's where the function is decreasing. Okay, I'll maybe highlight that just in red right now. So decreasing there and decreasing there. See that? And of course it's increasing. Let's use a different color. It's increasing on negative 7 over 2 to 3. Got that? Here it's increasing. And as well as from 2 to positive infinity. That's where it's increasing. So we are able to state the intervals of increase and decrease. That's what this question is asking you. And that's a big part of 4.1. Okay? Questions? Okay, so here in your textbook, the test for increasing or decreasing functions, this makes it official right here. If the derivative is greater than 0 for all x in an interval I, then the function itself is increasing. And here you go. All those derivatives are positive where the function is increasing. And likewise, where the derivative is negative for all x in the interval, then the function is decreasing. And that's the big deal with 4.1. That's what 4.1 is all about. So in example 1, I'll just briefly talk about example 1. Find the intervals on which the function is increasing and decreasing. So here's f of x. We first of all have to differentiate. You have to find the derivative. Then you have to factor the derivative because we need to do sign analysis. Now in this case, guess what? This is not that big of a deal. Really, there's only one factor, right? So you just got to kind of figure out when this is greater than 0 and when this is less than 0. And there's really only one point that it changes. Now does that make sense? Well, look at this. It's a parabola. It's a parabola that opens upwards. So you know the general shape. It's like this, right? So you're going to have one section of the domain where it decreases and one where it increases. So that's not that hard. Okay? So there's other examples that get a little bit more difficult, but look at this example too. This is no big deal either. You're given y, right here. You take the derivative of y. Come on now. Take the derivative of y. Can you factor that?
Oh,
You sure can. Take out a common factor, factor that trinomial. It's like you could do this in your sleep. It's baby stuff. And then you can do sign analysis. Now, if you have a factor of 3, just 3,
yeah.
okay, where is 3 equal to 0?
-3.
Nowhere. No. 3 does not equal 0 at any x value.
Oh, I see.
3 equals 3 all the time.
X plus.
So if you're going to include a constant on your sign analysis, you can, but it either has to be positive the whole time, if it's a positive, or a negative the whole time. So it's kind of like with this one here, because x does not change 3, they just dropped it. Because it's a positive value, it's not included. If this was a negative 3 that you pulled out, then you should include it in your sign analysis, because you're going to have to multiply a negative 3 times the others, right? Anyways, okay. So you're first going to be given a graph and asked where are the intervals of increase and decrease. Shouldn't be that hard, right? The function is what? And right here. It's increasing till about? Right about there. And what's happening from here to here? It is decreasing. And then from here to here again? Increasing. Okay? Now, notice a couple things. I don't know if they're asking you about this or not, but here's just a notice. What's the derivative at x equals 0? What's the derivative of the function at x equals 0?
0.
It's 0. What's the derivative of the function at x equals 2?
0.
No, it's not 0. Sorry, it's not 0. It's not 0.
It
It's not 0.
Isn't it?
I didn't mean to. I did not mean to react that way, but I'm surprised. I'm shocked. I'm appalled slightly.
Of the function at x equals 2.
What? Sorry.
Nothing. What was the question?
What is the derivative at x equals 2 here?
It's nothing.
It's not differentiable.
Yeah.
Remember
that's
that?
what I was meaning.
That's what I was saying.
That's what
Oh.
I was meaning.
0 is the same as it doesn't exist.
Oh.
Not
Same
true.
thing.
Okay? So it does not exist. The
Wait.
derivative does not
No,
exist
that's
here.
what I'm saying. I'm saying it's done. It's nothing. It's D
No,
and E.
no, I think you said 0. You did not say D and E,
I
you
didn't
said
say-
0. Okay,
I said
enough.
It's D and
Okay, so I'm going to give you your homework now. Any questions? Okay, so here's your sliding derivative here, and you can see where the function is
Are
increasing
you
from
gonna post
here
that?
to here. All of those are positive, except for right here.
Not differential.
Here. No, it's differentiable here.
Oh wait. Oh, it's just like
It's
Yeah.
either decreasing
So-
or increasing.
when is
Technically,
it
okay,
done?
whoa, watch. So technically, watch this. Technically, it's increasing from here to
0.
here, and then increasing from here to here.
Yeah.
So where it's 0, it's really not included in the interval. So you'd have to say from -1 to 0, then from 0 to 1.5ish, sure, is
Wait,
increasing.
So then when is it not different?
Well, this one, okay, it's not differentiable at the end points here,
Oh yeah.
but because these are smooth curves and not corners or cusps, then it's differentiable everywhere. So from round bracket -1 to round bracket +3, this is a continuous differentiable function.
You can post that.
Can we have a break? Look how far we've gotten through the textbook. We're doing so good.